Did a joke though that like it's like chest mounted, but it's pointed towards you.
Yeah.
Oh yeah. Like a 360 joke. Yeah. VR.
Yeah.
Okay. So where we ended last time was we had our definition of Gibbs free energy as a function of temperature and pressure, and the way that we got to this was by using the definition U minus Ts plus dV. Well, H is equal to U plus dV, so we're really saying that G is equal to H minus Ts. And this is what you've probably seen multiple times before in your chemistry classes or undergrad thermal. And we also talked about the fact that you're taking the first derivative of a thermodynamic potential, you get back the thermodynamic variables. If you take the second derivative, you get the physical properties which are measurable. So if we want to understand Gibbs free energy, or if we want to know it, then essentially we want to get the enthalpy and the entropy. And because we have this T, we can now say delta H is equal to the integral from T1 to T2 Cp dt. And similarly, we have Es is equal to Q over T is equal to H over T is equal to Cp T over T. That gives us delta S is equal to the integral from T1 to T2 Cp over T dt. So if we have good measurements of the heat capacity, we can extract the change in the enthalpy and the change in the entropy as we change temperature. So we're pumping energy into the system. Two notes. First is that this is again ideal gas. So if you want to know what's really happening in your system, you're going to have to be a little bit more resourceful in terms of the extra terms that get added into your expression. The second is that my notation, I have Cp versus the molar heat capacity. I tend to just drop those. It's important to follow units. It was the first time I saw thermodynamics where I got significantly confused was the fact that Gibbs energies or enthalpies would switch back and forth between molar and non-molar. So whatever you're working with, make sure the units match up. The Gibbs can either be a molar free energy, and the enthalpy can also be a molar, and the entropy can be molar expressions. So make sure you get those right. I'm just going to be going with Cp, but you can follow this through, and it should work out for you. So I should point out here that if we're using these, then we get delta G is equal to delta H minus delta S. So we can talk about the change in the free energy. as we change temperature. So if we can look at this graphically, I'll make sure that it's still in focus. And it's not in focus. Huh. That freezing the focus apparently doesn't work. Okay, so we can graphically look at this. Look for change in temperature. If we have that, have this being the Gibbs energy is equal to H minus Ts. In this case, at any particular temperature, the slope is equal to negative entropy. And then at T equals 0, here the enthalpy and the free energy are equal. So we can have the enthalpy plotted and the free energy and enthalpy have the same units. So we can plot them together as something like this. H. G is function temperature, and H function temperature. And because we have the enthalpy in terms of the heat capacity, we know that the slope of the enthalpy with respect to temperature is the heat capacity. So here, slope to capacity. And we also know that the distance between those two is equal to negative Ts. Or this way. H minus Ts gives you the free energy. So, talking about the heat capacities. Heat capacity versus temperature, it looks something like this. This is T equals 0. We're talking about a ideal gas. So all of this capacity to store thermal energy has to do with molecular vibrations. Gas. Going to solids, we'll still have phonons giving you a contribution to the heat capacity, but you'll also have electron contribution to, particularly if you have metals. Metals, the heat capacity is predominantly due to electrons being excited. But they're still going to have roughly the same shape. This point out here, where heat capacity approximately becomes linear, we call this theta D, the divide temperature. The divide temperature is the point where all of the available vibrational modes become active. So if you imagine a material which is extremely stiff, like diamond, at low temperatures, most of the atom is just sitting there. There's some vibration. As you heat them up, you get different vibrational modes. By vibrational modes, I'm talking about the the displacements of atoms relative to each other. So for example, if I had a crystal shaped like, let's draw a couple unit cells here. I have a crystal shaped like this. So there's a 2 atom basis in a unit cell. I'll draw these others in here. I can have atomic displacements that do things such as moving together in the same direction. We could have them moving in opposite directions. So one goes up, one goes down. I could have displacements in which this is going up, this is going up, this is going up, this is going down, this is going down. So you get periodicity to it. All of the possible ways that atoms can be displaced relative to each other, those are called our modes. And you can enumerate those. And we're not going to talk about that in this class, I don't think. But the important thing is, each one of these have a different vibrational frequency. And the vibrational frequency, the higher ones, require more energy to activate. As we're dumping energy in terms of increasing the temperature, we are activating those. At the Debye temperature, all the possible modes are active, which means we're no longer turning them on, but now they're basically constant. And there's typically a slope to this, but it's roughly linear. The Debye temperature is a really handy number to talk about. If someone says to you, I've got this material, the Debye temperature is 50 degrees Kelvin, and that's like lead. Lead's around 50 degrees. Or a person says, it's around 3,000, which is diamond. Right? The Debye temperature is a direct measure of the strength of the bonds, the stiffness of the material, and its relative brittleness, actually. That also tends to scale with the Debye temperature. The Debye temperature is also a useful parameter in several approximations. For example, approximating the melting temperatures and latent heats. They're also related to the Debye temperature. So this is our heat capacity. Heat capacities, they all have a general form, which is roughly Cp is a function of temperature. It's going to go as approximately as A plus B to the T plus C to the T minus 2. And that's the first 3 terms. Extending that, you can go plus D to the T squared. So A, B, C, D, these are coefficients. You go to your textbook, in the very back, in an appendix, you have 3 or 4 pages of nothing but heat capacities. And those are heat capacities which will give you the general shape. If you look at the heat capacities in your textbook, typically they'll only go out to these first 3 parameters. That's all you need. It's also worth noting that in your textbook, each of the heat capacities they give you is for a specific range. And that's because when we are measuring heat capacity, materials change phase. So for example, I'll draw it up here. I might have, let's say I'm looking at water, right? I might have a heat capacity. Delete this. Erase. We erase the board, we don't delete the board. Backspace all the time. Different people have different typing styles, and if you listen to my typing, I type fast and make lots of mistakes. It doesn't work so well on the chalkboard, whiteboard. This is ice. We can take that and we can roughly extend that if we have theoretical methods, and we do. We have water. We might have and vapor. So the range over which we have good measurements, we have good heat capacities. Fortunately, we typically have a little bit of overlap, which allows us to work without that overlap. You know, we can use theoretical methods, but it's not great. I shouldn't say that as a theorist, but they really aren't great. An interesting side note, we have this figure here. If you were to calculate the Gibbs free energy of water, just using the linear approximations for the heat capacity for ice, water, and vapor, when you calculate Gibbs as a function of temperature, draw it out. The important thing is that just using linear heat capacities and integrating them, you get the transition temperatures for melting and vaporization accurate to within plus or minus a half degree Fahrenheit, which is pretty cool. The fact that just using a linear heat capacity without this full expansion is that accurate. So if we say to ourselves then, what is the change in Gibbs free energy? We can do that, but we might want to have a little better measure. We might want to know, for example, what is the Gibbs free energy at this temperature? And we can do that if we have a reference that allows us to use the heat capacities and refer them for the heat capacities, the enthalpies, and entropies, and use them in an absolute sense. And we do have references. Reference H and S. So, one, elements in stable state by stable state, I mean the state that they appear naturally at that temperature. And that temperature is 298 K, H equals 0. Second, entropy I'm saying everything at T equals 0, K, S equals 0. That's, so a thermodynamic definition. So, what can we do with that? Well, we can go to these tables of tables of heat capacities and determine enthalpies and entropies. So, for example, O2 at T equals 370 K. Well, that means that the enthalpy is equal to the enthalpy at 298 of O2 plus the change in the enthalpy going from 298 to 373 O2. By definition, O2, this G, so the little subscript G's, and I can't remember if your textbook puts them above or below, but that specifies it as a gaseous state. So oxygen is in a stable state as a gas at 298, so by definition that term is 0, which means that our change in the enthalpy, which is going to give us our enthalpy, is going to be 298 to integral from 298 to 373 of 29.96 plus 4.18 times 10 to the minus 3t minus 1.67 times 10 to the 5 t to the minus 2 dt. And I took these from your textbook, and that gives us H is equal to 2239.5 joule per mole. So these heat capacities are molar. And we get the entropy. S is equal to a reference plus ds, the reference. We would love to go to 0. The problem is, for most elements, we don't have data down to 0 Kelvin. So most reference tables also give us the entropy at 298. So your textbook, there's also a table giving you this. So this is 298 to 373 O2G. This happens to be 205.1 joule per Kelvin mole. Right, so the units have to have a Kelvin in there. Plus the integral from 298 to 373, 1 over t times that dt. Inside that bracket is this, which I'm not going to write out. Draw an arrow in there. And this integral then is 6.699 joule per Kelvin mole. So that's dealing with elements. If we move from elements to compounds, we have a laugh track. Much talk about a solid state science class in which the class next door had something on. I don't know what it was, but they had mariachi music the entire lecture. It was a very festive lecture. Anyway, so let's talk about compounds. Okay, H2O has a vapor. The vapor and the gas. So we'll talk about that. And the enthalpy is H at 298 H2O gas plus integral Cp 298 to 373 dt. And this now is negative 241 kilojoule per mole. That's a fairly big number. That is the enthalpy of water at 298. And this term, that is the heat of formation. You want to think of having a system which is a box of water vapor. This contribution to the internal energy is the energy for the atoms to be bonded together. So if you want to dissociate H2O into its constitutive elements, that's where it comes from. And in general, we can talk about these enthalpies as a function of temperature, and they will also give us enthalpy of transformations. So for example, if I had the enthalpy versus temperature, and I picked silver, solid, 1, 2, silver, liquid with the latent heat of melting. This is HL. This is HS. If we have our melting temperature here, and that is our latent heat. Is basically saying if I have a liquid and I'm cooling down this liquid, and let's say I transition right at the melting temperature, which we know that doesn't happen, but let's say it does, then this much energy is going to be released into the system as I transition, or I shouldn't say it, I should say absorbed, because, no, it's released, sorry, it's released into the system as I cool down, as I change from being a liquid into a solid. What's more, that we also know that solidification doesn't occur at the melting temperature. Solidification, typically, we have some type of undercooling. And as you undercool, the energy which is given off is going to change as you undercool. So more undercooling is going to give you a larger deviation in the latent heat. All this okay so far? Okay. So we can also use similar diagrams to talk about reactions. So for example, we can talk about H2 gas plus 1/2 O2 gas becoming H2O gas. I'm treating it as vapor because I don't want to deal with the latent heat right now. If I do this, I have some H plus O2. I have some O, and at any given temperature, have the difference, applying the enthalpy, and this is the heat heat of reaction. So we talk about a chemical reaction being extropic or entropic. That's where that comes from, which whether it's absorbing energy during the reaction or giving it off. And I drew these two together because we're basically just adding them, right? The state functions can be added together. But to make it a little more explicit, right, we can talk about something such as EB plus 1/2 O2 is the solid O2 gas O solid. So here, marker here. Solid. I have O2 gas. And here I have O2 outside. Solid. Temperature. Now, the thing that complicates it is we can choose temperatures, but what if we choose a temperature which is greater than T melt? Right. Well, then that means that we have to transition to another curve, which is liquid. And in here, this distance is nothing. So if we were to put our reagents together, as I did on this plot, steal this figure. If this is our solid, then our products our reagents. We just add these two together, and then the difference So, I don't know if I said this in this class before, but I say it often, and it's been 10 years, so I lose track. Thermodynamics, once you have a very bare minimum of multivariable calculus and definitions of what, for example, a system is, what energy is, thermodynamics really just becomes a matter of bookkeeping. I mean, you can have multiple transitions, down here, oxygen solidifies, PbO is going to turn into a liquid up here somewhere. Here, PbO liquid. But all those things you can account for. You just have to be careful. And at least from my perspective, above all else, make sure you get the units right and get the signs right. The latent heat of melting versus the latent heat of solidification, it just comes out of your mouth different, but there's a sign difference. So it's the difference between walking north and walking south. So make sure that you get those correct when you're doing this type of calculation. Side note here, delta heat of reaction. How do you get the delta S of reaction? Well, S R N to delta H R X N over T star. So T star is the temperature where the reaction occurs. If you go to your textbook and have problems solving for free energies at different temperatures and free energies of reactions, your textbook gives a table of delta H of reactions, gives latent heats and gives enthalpies of transition or enthalpies of reaction. They do not have a table of entropies. So to get those, you just divide by the transition temperature that the table assigns. So all this is okay? It's a bit of a bear, but it works out pretty well. And say you'll spend, there are companies that have spent lifetimes mapping these out. Companies like Thermocalc that sell thermodynamic software, what you're paying them for is not the software, because the software is absolutely lousy in terms of its ease of use. You're paying them for the data. And they put all the data in one place, you click a button, and it gives you, heat capacity and the thermal coefficient of expansion of PBO as a function of temperature and pressure. But thinking of that, all of this was done under constant pressure. So we can do the same thing for pressure as we do for temperature. So what if we relax the constraint of pressure? So P. So that means that we have to go back and rethink what measurement we're working with. We have the H is equal to partial of enthalpy with respect to pressure, constant temperature, mole number, dP. We want that term. Because the H is equal to T ds plus V dP, we're able to say the partial of H with respect to pressure at constant temperature is equal to the temperature, the partial of entropy with respect to pressure, pressure at constant temperature plus V, and we've got a Maxwell relation. Hard for me to say that memorizing Maxwell relations is worthwhile because you can derive them so easily, but it's certainly handy to have a one-page set of notes in which you have these with you. Negative P. So this Maxwell relation going into there gives us negative T partial of V with respect to T P plus V, and using that the isobaric thermal coefficient of expansion is 1 over T partial of V with respect to temperature at constant pressure. then our change in enthalpy with change in pressure becomes negative T alpha V plus V, or H D P, a constant temperature is equal to V1 minus alpha T. Which means that pH is equal to V1 minus alpha T P. So you integrate that to get the change in the enthalpy, and the entropy is negative alpha V P. And these two let you find the effect of changing the pressure, which means that we're changing both the temperature and the pressure at the same time. Change the temperature and the pressure at the same time, then delta H equal to the change from temperature 1 to temperature 2, Cp dt plus the integral from pressure 1 to pressure 2, V1 minus alpha T P, and the change in the entropy is the integral from 1 over T1 to T2, Cp over T dt plus the integral from pressure 1 to pressure 2, negative alpha V dP. Changing colors, although that marker is pleasant to use. Just talking about pressure terms. By the way, temperature and the pressure are separated. This is indicative of the fact that the path we choose, whether we change temperature first, then pressure, or pressure first, then temperature, it doesn't matter. It's just the ending points. They're not coupled together. We just talk about these. The integral, and I'm going to do this P1, P2, N, R, T over P, 1 minus 1 over T, T, P, 0, and delta S is equal to integral from P1, P2, NR negative, NR over P, P is equal to negative NR natural log P2 over 1. So when we change the pressure in an ideal gas, there's no change to the enthalpy for changing pressure. And that's because in an ideal gas, the molecules don't interact. They don't see each other. In the case of the enthalpy, though, we do have a change because, well, the short answer is because we're changing the number of possible configurations of molecules as we increase the pressure. So we can account for that in terms of the give us the configurational okay. Is that all clear? Cool. Okay. Well, that's all I've got for this week, and we'll work problems on Friday, have a quiz on Monday. This is going to be good problems to work. You can see. Have a great one today.